Hi, my name is Andrew Hodges, and I'm here today to tell you how calculus relates to my major, civil engineering. Civil engineers use calculus in many different ways. They use derivatives to derive the basic fluid functions, which are used to describe how, buildings are fit in water. And then they also use vectors to describe forces, so that way they can tell whether or not their creations are viable. So I'm going to solve this problem here from our engineering mechanics book. The frame shown supports part of the roof of a small building. Knowing the tension in the cable is 150 kilonewtons, determine the reaction at the fixed end E. That is this point right here, and at this point there is an X component and a Y component. Now also, this is our tension right here. This cable here is 150 kilonewtons. There's also an X component and a Y component at this point too. Now, first we're going to solve for these two triangles. They're similar triangles, so we can solve our missing variables. First, we're going to find this length here from D to F, which we're just going to use the Pythagorean theorem, which is going to be -6 squared plus 4.5 squared. And that's going to give us 7.5 meters. So we set up our triangle. We have this here. This is our tension Y component, which is -6 meters. This is 4.5 meters, which is our tension X component. This is 7.5 meters, which is our total tension, which is also 150 kilonewtons. So now we're going to set up our proportions to solve for Tx and Ty. So we're going to set Tx over the total tension, which is going to be 150 kilonewtons. And then we're going to set that equal to the length of Tx, which is 4.5 meters, over the total length of this hypotenuse, which is 7.5 meters. And then we multiply here, divide here, and we get the tension in X is equal to 90 kilonewtons, and that is in I hat. Now we're going to solve for Ty, which we're going to do the same thing. We're going to set the tension, magnitude of the tension of Y over 150 kilonewtons, and set that equal to -6 meters over 7.5 meters. And then we do the same thing, multiply here, divide here, and we get the magnitude of the tension is equal to -120 kilonewtons J hat. Now to save space, I'm going to write these values over here. So we're going to get the magnitude of the tension X is equal to 90 kilonewtons I. And then we're going to get the magnitude of tension Y is equal to -120 kilonewtons J. Now at this point, since this is a very basic problem and we're not taking into account outside forces like wind, this is an equilibrium, and that means all the forces add up to 0 and all the moments add up to 0, and I'll describe what a moment is later. So first, we're going to start with all the forces, the sum of the forces in X, which is equal to 0. So this is going to equal, in this problem, there's only two forces in X. That's the EX component and the tension X component. So that's going to equal the magnitude of the EX component plus the magnitude of the tension X component, which, if you remember, is 90 kilonewtons I hat. So we write that right here. Now we solve for the magnitude of E of X, which is just -90 kilonewtons I hat. So we're going to write that over here. So at this point, now we have the x components added up, we're going to add up the y components. So this is the force in y of the whole frame, and there's 4 20 kilonewton forces here. Now these are negative because they are going down, so that's negative j hat. So it's going to be 4 times negative 20 kilonewtons j hat plus the EY component and the tension Y component. And those are all equal to 0. So we're going to bring this down to negative 80 kilonewtons j hat plus the magnitude of EY plus, and if you remember, our tension Y is negative 120 kilonewtons j hat. Now we just solve for the magnitude of EY, so that makes this 200 kilonewtons j hat equals magnitude of EY. Now we're going to have to find the moment at this point. So since we had to add them up, we had to move all of these forces to this point, and in doing so, we created a moment. And now to find a moment, you cross the distance vector of that force with the total force, the forces. So in doing so, we're going to have this equation here. We're going to have this equation here. The sum of the moments in E is equal to 0, which is equal to, now for these, this is going to be our origin, so this is going to be our 0, 0 point. We have to move the forces from here, with this being our starting point, or our starting point. So using the distance formula, we do final minus initial, which this total distance for point A is going to be negative 7.2 meters I hat. And that's also with the component of 3.7 meters, 3.75 meters j hat. And we're going to cross that with a negative 20 kilonewtons j hat. Now we're going to add the rest of these forces using the same methods. So that's going to be negative 5.4 meters plus 3.75 meters. And this first one was in j hat, or I hat, and this one's in j hat. We're going to cross that with another negative 20 kilonewtons j hat for this force here. We're going to do the same here and here. So that's plus negative 3.6 meters I hat plus 3.75 meters j hat crossed with negative 20 kilonewtons j hat plus negative 1.8 meters I hat plus 3.75 meters j hat crossed with another negative 20 kilonewtons j hat. Now we're finally to this force here. In doing that, we're going to add this distance formula here. Since it's at this point, we only have to worry about the x component, which is going to be 4.5 meters I hat. And we're going to cross that with our x component and our y component, which is going to be 90 kilonewtons I hat plus negative 120 kilonewtons j hat. And after all this, we also have our moment at E. So we have this. So let me remind you that, if you don't know, crossing an I hat with an I hat, a J hat with a J hat, or a K hat with a K hat, that equals 0. So at this point, we have a J hat here crossed with a J hat here, so we can eliminate this. And I'm going to go ahead and eliminate all those from the whole equation. And at this point, we were crossing an X distance, which is an I hat, with a X force and a Y force. So we're going to cross out the X force to simplify the problem. Now doing this math, adding this all up, which is still equal to 0, we have this. 144 kilonewton meters K hat. And that's from an I hat crossed with a J hat equals a K hat. Plus 108 kilonewtons meters K hat plus 72 kilonewtons meters K hat plus 36 kilonewton meters K hat minus 540 kilonewton meters K hat, and this minus one came from the tension force, plus the moment force at E. Now, solving for E here at this point, we can add all of these up and move it to the other side, and that leaves us with 180 kilonewton meters K hat at the moment of E. Now, solving this formula just determines how, if this force would be able to, if this frame could be able to hold itself up. This isn't taking into account any like wind or any other forces like that. I hope I was able to show you how civil engineers use vectors. Thank you for watching.